On the morning of February 4, 1943, a crippled Boeing B-17E Flying Fortress limped across the Pacific sky above the Dutch East Indies, trailing smoke from two dying engines. Inside the fuselage, Captain Harold Johnson and his crew of 9 fought desperately to keep their aircraft airborne, but the mathematics of altitude and fuel had already sealed their fate. The massive 4-engine bomber, which had departed from Port Moresby hours earlier on a reconnaissance mission, began its inevitable descent toward Japanese-occupied Java. For the American airmen, this was the end of their war. For Imperial Japan's aeronautical engineers, it was about to become the beginning of a profound revelation. The B-17 crash-landed in a rice paddy near Surabaya, its belly scraping across the waterlogged earth before coming to rest like a beached whale. Japanese infantry units arrived within the hour, securing the site and taking the stunned American crew into custody. But while the prisoners were led away to internment camps, the aircraft itself became the prize. Word traveled quickly through Japanese military channels. An intact American heavy bomber, one of the legendary flying fortresses that had already earned a fearsome reputation, now sat in Japanese hands. Within 3 days, a team of engineers from the Technical Air Arsenal at Tachikawa arrived at the crash site. Leading them was Commander Yoshio Komatsu, a veteran aircraft designer who had worked on several of Japan's frontline fighters. Komatsu had heard the intelligence reports about the B-17's capabilities, its ability to absorb tremendous damage and continue flying, its defensive armament of 13 machine guns, its operational ceiling that exceeded anything in the Japanese bomber fleet. But nothing had prepared him for what he would discover when his team began their systematic examination of the aircraft. The first thing that struck Komatsu as his engineers pried open access panels and crawled through the bomber's interior was the sheer complexity of the systems. The B-17 wasn't simply a flying machine, it was a coordinated symphony of interconnected technologies working in concert. According to historical accounts from the Japanese Technical Air Intelligence Center, documented by aviation historian Robert Mikesh, the examination team worked around the clock for 3 weeks, photographing, measuring, and documenting every aspect of the bomber's design. The fuselage, despite the crash damage, revealed construction techniques that astounded the Japanese engineers. The aircraft employed a semi-monocoque structure with formers and stringers supporting an aluminum skin, but it was the precision of the manufacturing that caught their attention. Every rivet, every seam, every structural joint demonstrated a level of mass production capability that Japan's cottage industry approach to aircraft manufacturing had never achieved. The wings alone contained over 47,000 separate parts, yet they had been assembled with tolerances measured in thousandths of an inch. But it was when Komatsu's team reached the cockpit that they encountered something that would fundamentally challenge their understanding of aviation technology. The instrument panel before them wasn't just a collection of gauges and switches. It was an automated command center that spoke to an entirely different philosophy of aircraft design. Commander Komatsu stood in the cramped cockpit of the captured B-17, his eyes scanning the bewildering array of instruments, switches, and controls that covered nearly every surface. His colleague, Lieutenant Commander Saburo Nakajima, a specialist in aircraft instrumentation, crouched beside him, carefully sketching the layout of the pilot's panel. What they were witnessing would later be documented in reports sent to the Imperial Japanese Navy's Aviation Bureau, records that would reveal just how far behind Japan had fallen in aviation automation technology. The turbo supercharger system immediately captured the engineers' attention. Unlike Japanese bombers, which required manual adjustments of engine controls as altitude changed, the B-17 featured General Electric turbo superchargers that automatically maintained engine power at high altitudes. Each of the 4 Wright R-1820 Cyclone engines possessed its own supercharger, regulated by an automatic system that compressed intake air to maintain sea-level atmospheric pressure even at 25,000 feet. Nakajima discovered that these superchargers operated through an intricate network of pressure sensors, oil lines, and mechanical regulators that required virtually no pilot intervention. "In our aircraft," Nakajima wrote in his technical assessment, "the pilot must constantly monitor manifold pressure, adjust throttle settings, and manage fuel mixture as altitude changes. This American bomber does these calculations automatically. The pilot simply sets his desired altitude, and the aircraft maintains optimal engine performance. The hydraulic systems proved equally revelatory. The B-17 employed hydraulic power for landing gear retraction, flap operation, and brake application, features that Japanese heavy bombers either lacked entirely or operated through exhausting manual mechanisms. The Americans had developed a reliable hydraulic pump system driven by each engine, with automatic pressure regulators and backup systems that ensured redundancy. When one engineer accidentally triggered the landing gear lever during the examination, the massive gear assemblies began to lower smoothly despite the aircraft resting on its belly, powered by auxiliary hydraulic pumps. The team watched in amazement as centuries of mechanical advantage were demonstrated through pressurized fluid flowing through precision-manufactured tubing. The electrical system represented another quantum leap in automation. The B-17 possessed multiple generators, voltage regulators, and an electrical distribution system that powered everything from gun turrets to heated flight suits. According to historical documentation preserved in the Japanese Defense Archive, the examination team counted over 4 miles of electrical wiring running throughout the aircraft. Most remarkably, this wiring followed a color-coded standardization system that allowed for rapid troubleshooting and repair, something Japanese aircraft completely lacked. Every wire could be traced, every connection identified through a systematic numbering scheme that suggested a level of manufacturing planning that seemed almost extravagant to the Japanese engineers. The oxygen system exemplified the American approach to crew survivability at high altitude. Rather than the simple bottled oxygen systems used in Japanese bombers, the B-17 featured a sophisticated demand-type oxygen delivery system that automatically adjusted flow based on altitude. Regulators sensed ambient pressure and delivered appropriate oxygen concentrations to each crew member's mask. For Japanese bomber crews, who often suffered hypoxia during high-altitude missions due to inadequate oxygen supplies, this automated life support system represented not just technological sophistication, but a fundamentally different attitude toward crew welfare. Perhaps most impressive was the aircraft's electrical bomb release system. Japanese bombers of the period employed mechanical cable systems to release bombs, requiring significant physical effort from the bombardier and offering limited precision. The B-17's bombardier operated an electrical system interfaced with the Norden bomb site, a device so sophisticated that the examination team was ordered not to study it in detail, as intelligence indicated it contained classified optical and mechanical computing elements. The bomb release mechanism automatically compensated for aircraft speed, altitude, and wind drift, executing release sequences electronically with timing precision measured in milliseconds. Komatsu compiled his findings into a comprehensive report that would circulate among Japan's highest aviation authorities. By the end of the first month of examination, the captured B-17 had been carefully dismantled and transported to the Tachikawa facility outside Tokyo, where Commander Komatsu assembled a larger team of specialists to conduct deeper analysis. What emerged from their investigation went beyond simple technical admiration. It revealed a fundamental divergence in manufacturing philosophy between American and Japanese aviation industries. This realization, documented in reports from the spring of 1943, would haunt Japanese military planners for the remainder of the war. Engineer Hiroshi Tanaka, who specialized in production methodology, focused his attention on the manufacturing techniques evident in the B-17's construction. Every component told a story of mass production at a scale Japan had never attempted. The wing ribs, for instance, were stamped from aluminum sheets using high-tonnage presses, creating identical parts by the thousands. Japanese aircraft manufacturers, in contrast, still relied heavily on hand-forming techniques, where skilled craftsmen individually shaped each component. While this artisanal approach produced beautiful aircraft, it meant that parts were rarely interchangeable between supposedly identical machines. The standardization extended to the smallest details. Fasteners throughout the B-17 conformed to American national standards, meaning that bolts, nuts, and screws from any American manufacturer would fit perfectly. When Tanaka's team examined Japanese aircraft for comparison, they discovered that even within a single factory, fastener specifications might vary between production batches. Mechanics working on Japanese bombers often needed to hand-fit components, filing and adjusting until parts mated properly, a process that consumed hundreds of hours per aircraft. According to historical research compiled by aviation historian Osamu Tagaya in publications examining Japanese wartime aviation technology, the American approach to tolerances particularly impressed the examination team. The B-17's engine mounts demonstrated precision machining that allowed engines to be removed and replaced in hours rather than days. Ball bearings throughout the aircraft, in control surfaces, landing gear, and turret mechanisms, were manufactured to specifications that Japanese bearing manufacturers had declared impossible to achieve in mass production. One engineer noted in his report that a single B-17 contained more precision bearings than an entire squadron of Japanese bombers. The electrical wiring harnesses revealed another dimension of American manufacturing prowess. Rather than individual wires run separately throughout the aircraft, Boeing employed pre-assembled wiring harnesses manufactured off the aircraft and then installed as complete units. Each connector used standardized plugs that could be disconnected and reconnected without soldering. This modular approach meant that damaged sections could be replaced rapidly in field conditions. Japanese aircraft, meanwhile, had individually routed wires that were often soldered directly to components, making field repairs nightmarishly complex. The hydraulic components demonstrated similar mass production sophistication. Pumps, valves, actuators, and tubing fittings were manufactured to such precise standards that they were truly interchangeable. Any hydraulic pump from any B-17 could be installed in any other B-17 without modification. When the examination team disassembled the hydraulic pumps, they found precision-ground internal components with surface finishes that exceeded anything in Japanese hydraulic technology. The seals were synthetic rubber compounds that maintained their properties across extreme temperature ranges, unlike the natural rubber seals in Japanese systems that hardened in cold weather and softened in heat. Commander Komatsu came to understand that the B-17 represented not just advanced engineering, but advanced industrial organization. The aircraft was designed from the beginning for mass production, with tooling, fixtures, and assembly procedures planned before the first prototype flew. Boeing had created manufacturing infrastructure, massive hydraulic presses, precision jigs, automated drilling machines that enabled production rates of dozens of aircraft per month from a single factory. Japan's aviation industry, operating under entirely different constraints, had pursued a different path. As spring gave way to summer in 1943, Commander Komatsu's technical team completed their exhaustive examination of the captured B-17. Their final report, running to over 300 pages with detailed drawings and photographs, arrived on the desks of Japan's military aviation leadership in late June. The document's conclusions were sobering. The gap between American and Japanese aviation technology was not merely years, but represented fundamentally different industrial capabilities. The question facing Japanese planners was whether any of the B-17's sophisticated automation could be adapted to Japanese production, or whether the underlying manufacturing infrastructure simply didn't exist. Vice Admiral Isoroku Yamamoto, who had studied at Harvard University and served as a naval attaché in Washington during the 1920s, had long warned about American industrial capacity. When presented with excerpts from Komatsu's report, Yamamoto reportedly stated that he had seen automobile factories in Detroit that could be converted to aircraft production overnight, factories larger than entire Japanese aircraft companies. The B-17, he understood, was not an exceptional achievement of a few brilliant engineers, but the product of an entire industrial ecosystem. The Nakajima Aircraft Company, Japan's largest aviation manufacturer, attempted to implement some of the standardization principles discovered in the B-17 examination. Engineers developed plans for modular wiring harnesses and standardized fastener specifications for the company's new bomber designs. However, these initiatives foundered on practical obstacles. Japanese machine tool manufacturers could not produce the high-precision equipment necessary for mass production of interchangeable parts. The nation's bearing industry lacked the metallurgical expertise to manufacture the high-grade steel bearings that American automation systems required. Even basic materials posed challenges. Aluminum alloys matching American specifications required refining processes that Japanese smelters had not mastered. The turbo supercharger system particularly frustrated Japanese engineers attempting to replicate it. According to post-war technical analyses documented by aviation researcher René Francillon, Japan attempted to develop domestic turbo superchargers throughout the war, but never achieved the reliability or performance of American systems. The problem lay not in understanding the principles — Japanese engineers grasped the thermodynamics perfectly well — but in manufacturing components that could withstand extreme temperatures and pressures for hundreds of operating hours. The turbine wheels required special high-temperature steel alloys that Japan struggled to produce in quantity. The precision bearings that allowed turbines to spin at 50,000 revolutions per minute were beyond Japanese manufacturing capability. Lieutenant Commander Nakajima proposed a series of incremental improvements to Japanese bomber designs based on B-17 features. His recommendations included hydraulic landing gear systems, electrical bomb releases, and improved oxygen delivery. Yet implementing even these simple upgrades proved challenging. The hydraulic systems required reliable pumps, precision-machined cylinders, and synthetic seals, all requiring manufacturing capabilities and materials in short supply. The electrical systems needed copper wire, which by 1943 was being rationed for military electronics. The oxygen systems required pressure regulators manufactured to specifications that few Japanese firms could meet consistently. Perhaps most telling was the philosophical gulf that the B-17 examination revealed. American aircraft design prioritized pilot workload reduction and crew survivability. The automation systems existed to allow pilots to focus on navigation and combat, rather than constant manual engine management. The defensive armament protected the crew through overwhelming firepower rather than maneuverability. The structural redundancy allowed the aircraft to sustain damage and still complete its mission. These design choices reflected an industrial system wealthy enough to build aircraft with thousands of pounds of excess equipment, devoted to automation and crew protection. Japanese design philosophy, shaped by resource constraints and different tactical doctrines, emphasized performance efficiency and offensive capability over automation and survivability. Japanese bombers were lighter, more maneuverable, and carried proportionally larger bomb loads relative to their size. They achieved this performance by eliminating systems that Americans considered essential. Armor protection was minimal, defensive armament was reduced to save weight, and automation was sacrificed in favor of pilot skill. A skilled Japanese crew could coax remarkable performance from their aircraft, but this approach placed enormous burdens on aircrews and resulted in far higher casualty rates when aircraft sustained damage. The captured B-17 sat in a hangar at Tachikawa, its examination complete but its lessons only partially absorbed. Throughout the summer and autumn of 1943, Commander Komatsu traveled across Japan, presenting his findings on the captured B-17 to various military and industrial audiences. His lectures, delivered to packed rooms of engineers and military officers, contained a message that many found uncomfortable. Japan's aircraft industry was not simply behind America's in automation technology. It lacked the industrial foundation necessary to close that gap during wartime. This reality would have profound implications for the thousands of Japanese aircrew members who would fly combat missions in the war's final years. At Kasumigaura Air Base, Komatsu addressed a group of bomber pilots and navigators who were training on the Mitsubishi G4M, known to the Allies as Betty. He described the B-17's automated systems, explaining how American pilots could maintain formation at 25,000 feet, while the turbo superchargers automatically adjusted engine performance, how hydraulic systems powered controls with minimal physical effort, and how the oxygen delivery system ensured crew alertness. The Japanese pilots listened with professional interest, but many understood the implications. Their G4M bombers required constant manual adjustment of engine controls, fuel mixture settings, and propeller pitch. At high altitude, pilots fought control sticks stiffened by air pressure, while simultaneously managing engine parameters that American pilots simply didn't think about. The oxygen system comparison proved particularly stark. Lieutenant Kenji Hayashi, a veteran bomber pilot with over 500 combat hours, later wrote in his diary about Komatsu's presentation. Hayashi described missions where crew members had succumbed to hypoxia because oxygen bottles ran empty or regulators malfunctioned. Without the automated pressure compensation of American systems, Japanese crews had to manually adjust oxygen flow valves as altitude changed. In the stress of combat, with anti-aircraft fire bursting around the aircraft and fighters attacking. These manual adjustments were often forgotten until symptoms of oxygen deprivation, confusion, euphoria, loss of consciousness made correction impossible. The defensive armament comparison highlighted another dimension of crew vulnerability. The B-17 possessed 13 Browning M2 machine guns arranged in positions providing overlapping fields of fire: nose, tail, dorsal, ventral, and waist positions, many mounted in power-driven turrets that used electrical motors and sophisticated targeting systems to track enemy fighters. According to historical accounts from aviation researcher Donald Miller's research into 8th Air Force operations, these defensive systems allowed B-17 formations to create what bomber crews called mutual support zones, where concentrated fire deterred fighter attacks. Japanese bombers, in contrast, carried far lighter defensive armament to save weight. The G-4M Betty, for instance, had only 4 manually operated machine guns with limited fields of fire. Gun positions lacked power assistance, requiring gunners to physically traverse and elevate their weapons while being buffeted by slipstream through open windows. When American P-38 Lightning or Grumman F-6F Hellcat fighters attacked Japanese bomber formations, the defensive fire was often inadequate to deter determined attacks. The casualty rates reflected this disparity. While B-17 crews certainly suffered losses, Japanese bomber crews faced mortality rates that were substantially higher during equivalent operations. The structural resilience differences profoundly affected crew survival. American aircraft designers had incorporated what they termed damage tolerance into B-17 design. Redundant control systems meant that severed cables or damaged actuators didn't necessarily mean loss of control. Self-sealing fuel tanks and armored protection around critical systems reduced the likelihood of catastrophic fire or explosion. The robust structure could absorb tremendous battle damage, engine losses, control surface damage, even fuselage sections blown away, and still potentially return its crew safely. Japanese bombers, optimized for range and speed through weight reduction, possessed none of these survivability features. A single cannon shell hit could prove catastrophic. Fuel tanks, unprotected to save weight, ignited readily when hit by incendiary rounds. The G-4M earned a grim nickname among Japanese crews, the Flying Lighter. Pilot Hayashi's diary contains harrowing accounts of watching sister aircraft explode in midair after taking what appeared to be relatively minor damage. Entire crews lost in an instant because weight-saving measures had eliminated redundancy and protection. The automation gap affected training efficiency as well. American pilot training programs could focus on tactical procedures, navigation, and bombing techniques because the aircraft's automated systems handled many routine functions. Japanese pilots required extensive training simply to manage their aircraft's manual systems competently, mastering the constant adjustments required at different altitudes, learning to coordinate engine management while maneuvering in combat, developing the physical stamina to fight heavy control forces during multi-hour missions. These demands consumed training time and cognitive capacity that American pilots devoted to combat effectiveness. By early 1944, the industrial limitations that Commander Komatsu's examination had revealed forced Japanese aviation planners to confront an uncomfortable reality. They could not replicate American automation technology, so they would need to adapt their tactics and training to compensate for the technological gap. This acknowledgement sparked debates across Japanese military aviation that would influence operations throughout the war's final stages. The captured B-17, meanwhile, found a new purpose as a training tool, its sophisticated system serving as an educational resource for Japanese pilots who might encounter similar aircraft in combat. Captain Minoru Genda, an influential tactician who had helped plan the Pearl Harbor attack, studied Komatsu's reports with particular interest in the B-17's defensive capabilities. Genda recognized that Japanese fighter pilots needed to understand the automated fire control systems they faced. The American power turrets, with their electrical tracking systems and centralized fire control, created defensive zones that required specific attack approaches to penetrate effectively. He arranged for the captured B-17 to be refurbished for ground demonstration, allowing fighter pilots to observe the turret systems in operation and develop attack tactics that exploited gaps in coverage. The demonstration sessions at Kashiwa Air Base proved educational in unexpected ways. Fighter pilots who examined the B-17's turret systems discovered that American gunners benefited from significant technological assistance. The turrets used gyroscopic stabilization to smooth out aircraft motion, making accurate tracking easier. Computing gun sights automatically calculated lead angles based on target speed and range. The hydraulic power traverse systems allowed gunners to track targets smoothly without fighting mechanical resistance. One Japanese fighter pilot, Lieutenant Saburo Sakai, a decorated ace whose post-war memoir, Samurai, provided detailed accounts of his combat experiences, wrote that understanding these systems explained why American bomber defensive fire was so effective. The technology amplified gunner skill in ways that manual systems could not match. Japanese aviation authorities attempted several programs to improve automation in domestic aircraft, with mixed results. Mitsubishi developed a prototype hydraulic landing gear system for new bomber variants, but the chronic shortage of high-grade hydraulic fluid forced designers to revert to manual systems for production aircraft. Nakajima engineers created an electrical bomb release mechanism similar to American systems, successfully implementing it on some Ki-49 Helen bombers. However, the copper wire requirements proved prohibitive for widespread adoption, and most aircraft retained mechanical release systems. The oxygen system improvements achieved more success. Inspired by the B-17's automated delivery system, Japanese manufacturers developed improved pressure regulators that required less manual adjustment, though they never achieved the fully automatic operation of American systems. These incremental improvements reduced hypoxia incidents, though Japanese bomber crews continued to face oxygen-related challenges that American crews rarely encountered. According to post-war technical assessments compiled by Allied intelligence teams, Japanese oxygen systems circa 1944 were roughly equivalent to American systems from the mid-1930s, functional, but requiring far more crew attention and management. Some adaptations focused on training rather than technology. The Imperial Japanese Navy instituted enhanced instrument flight training programs, recognizing that American automation allowed operations in weather conditions that Japanese aircraft could not safely navigate. While Japanese pilots could not enjoy the same automated assistance, improved training in manual instrument flying partially compensated, allowing operations in marginal weather that previously would have grounded missions. Similarly, navigation training emphasized dead reckoning and celestial navigation skills to compensate for the lack of automated navigation aids that American aircraft increasingly carried. The industrial priorities behind these choices became clearer as the war progressed. By mid-1944, Japan faced critical shortages of strategic materials, aluminum, copper, high-grade steel, synthetic rubber, that made sophisticated automation systems increasingly untenable, regardless of technical capability. Aircraft designers were forced to pursue simplification rather than sophistication, creating designs that required fewer precision parts and less strategic material. The lessons of the B-17 examination remained relevant, but as aspirational targets rather than immediate implementations. Captain Komatsu himself transitioned from technical examination to operational analysis, applying his understanding of American automation to intelligence assessment. When new American bomber types appeared, the B-24 Liberator, and later the massive B-29 Superfortress, Komatsu's team analyzed their capabilities through the framework established by the B-17 examination. Each new American type demonstrated further automation advances: improved fire control, more sophisticated engine management systems, pressurized crew compartments with automated climate control. The technological gap was not closing, it was widening. The captured B-17 remained at Kashiwa, increasingly obsolete as American aviation technology advanced, but still valuable as a tangible reminder of industrial capabilities Japan could not match. On November 24, 1944, the technological gap that Commander Komatsu had documented became devastatingly apparent when the first B-29 Superfortress bombers appeared over Tokyo. The appearance of these massive aircraft, flying at altitudes beyond the reach of most Japanese fighters, represented the culmination of American industrial might and automation technology. For Komatsu and his team, who had spent months studying the B-17 systems, The B-29 was a sobering demonstration that American aviation had continued advancing, while Japan struggled simply to maintain production. The B-29 embodied automation concepts that had been mere hints in the B-17. The pressurized cabin eliminated the need for oxygen masks below 30,000 feet, maintaining a shirt-sleeve environment through automated pressure controllers. The remote-controlled defensive turrets, operated by gunners using periscope sights and computing fire control systems, represented a quantum leap beyond the B-17's manually aimed guns. The engine management systems employed electronic controls that automatically adjusted superchargers, fuel mixture, and propeller pitch across a wide range of flight conditions. The aircraft even featured a primitive autopilot system that could maintain altitude, heading, and speed without pilot intervention, allowing crews to focus on navigation and bomb delivery during the long overwater flights from Saipan to Japan. When a damaged B-29 made an emergency landing on Japanese-held airfields in western China in late 1944, Komatsu received orders to conduct another examination. The experience proved deeply discouraging. The technological sophistication evident in every system exceeded anything he had seen in the B-17. The engine analyzer panels could diagnose engine problems automatically, alerting engineers to issues before they caused failures. The bombing system integrated with automated navigation equipment, creating a sophisticated attack system that reduced crew workload dramatically. The fire control system for the defensive turrets employed analog computing technology that automatically calculated lead, deflection, and range, presenting gunners with pre-computed aiming solutions. According to historical documentation from post-war technical intelligence reports compiled by American investigators, the Japanese examination of the B-29 confirmed what many already suspected. Japan lacked the industrial capacity to develop equivalent systems. The engines alone, massive Wright R-3350 duplex cyclone radials producing 2,200 horsepower each, represented metallurgical and manufacturing achievements beyond Japanese capability. The pressurization system required precision seals and pressure vessels that Japanese manufacturers had never produced. The electronic fire control demanded vacuum tube technology and electrical systems of a sophistication that Japan's electronics industry had not mastered. Lieutenant General Takeo Yasuda, head of the Army Air Arsenal, reviewed Komatsu's B-29 assessment with a perspective shaped by 2 years of industrial decline. The strategic bombing campaign against Japanese industry had destroyed or damaged many manufacturing facilities. Raw material shortages had forced quality compromises throughout the production chain. Skilled workers had been drafted into military service or killed in air raids, leaving factories staffed by inexperienced replacements. Even if Japanese engineers fully understood American automation technology, the industrial foundation necessary to implement it was eroding rapidly. The contrast between American and Japanese aviation technology by late 1944 reflected broader industrial trajectories. American aircraft factories had expanded enormously since Pearl Harbor, with production techniques continuously refined for efficiency. Boeing's Renton plant alone produced more B-29 bombers per month than Japan's entire heavy bomber output. The automation and mass production techniques that had so impressed Komatsu in the B-17 examination had been further perfected, allowing American manufacturers to build increasingly sophisticated aircraft at accelerating rates. American factories employed extensive mechanization, automated drilling machines, power riveting tools, hydraulic presses that reduced manual labor requirements while improving consistency and speed. Japanese aircraft production, despite heroic efforts by workers and managers, struggled against multiplying obstacles. Allied submarine warfare had severed supply lines for strategic materials. The lack of mechanization meant that production scaled linearly with workforce size, and the workforce was shrinking due to casualties and malnutrition. Quality control suffered as experienced inspectors were reassigned or killed. Aircraft rolled out of factories with defects that would have been caught earlier. Engine failures became common. Hydraulic systems leaked. Electrical problems plagued new aircraft. The automation that might have compensated for workforce losses remained unattainable. Komatsu's final report on the B-29 examination, completed in January 1945, contained a stark assessment. He concluded that attempting to replicate American automation technology was futile given current Japanese industrial capabilities. Instead, he recommended focus on tactical adaptations, developing attack methods that exploited any B-29 vulnerabilities, improving Japanese fighter performance through simplification rather than sophistication, and preparing for defensive operations that accepted Japan's technological disadvantages. The report circulated among senior officers as American bombing raids intensified, its pessimistic conclusions uncomfortably aligned with the reality visible in Japan's burning cities. The two captured American bombers, the B-17 at Kashiwa and the B-29 in western China, stood as monuments to industrial capabilities Japan could observe but not equal. In the final months of the war, as American B-29s burned Japanese cities in massive incendiary raids, Commander Komatsu reflected on the journey that had begun with the captured B-17 examination in February 1943. His technical reports, now archived in military files that few consulted amid the chaos of total war, represented a peculiar form of prophecy, accurate predictions of industrial inadequacy that Japan's leadership had acknowledged but could not address. The automation gap he had documented so thoroughly had proven decisive not through any single engagement, but through the cumulative effect of thousands of missions where American technological advantages compounded into overwhelming aerial superiority. The fate of the captured B-17 itself demonstrated the war's progression. American bombing raids in early 1945 damaged the Kashiwa facility where the aircraft had been stored. In March, with U.S. forces advancing across the Pacific and strategic materials desperately scarce, orders came to dismantle the B-17 for salvage. The aluminum alloy went to fighter production. The instruments were harvested for whatever value they might provide, and the sophisticated automation systems that had so impressed Japanese engineers were cut apart for scrap metal. By April, nothing remained of the aircraft that had sparked such profound technical revelation. Captain Komatsu survived the war and participated in post-war technical exchanges with American aviation experts. These conversations, documented in occupation records, revealed that American engineers had been largely unaware of the detailed Japanese examination of captured B-17s. To American designers, the automation systems that so impressed Japanese engineers were simply standard production features, refined through continuous improvement programs, but not considered particularly remarkable. This perspective highlighted the gulf between the two industrial systems. What represented cutting-edge sophistication to one nation was routine manufacturing to the other. Post-war analyses, conducted by teams of American technical intelligence officers examining Japanese aviation facilities, confirmed much of what Komatsu had reported. Japanese aircraft manufacturers had attempted to implement various automation features, but had been consistently thwarted by material shortages, manufacturing limitations, and lack of supporting infrastructure. Some attempts at hydraulic systems had been abandoned due to seal failures. Electrical systems had proven unreliable due to insulation materials that degraded quickly. Turbo supercharger programs had consumed enormous resources while producing systems that failed frequently in service. The industrial ecosystem that enabled American automation, specialty steel producers, precision bearing manufacturers, synthetic materials companies, advanced machine tool builders, simply didn't exist at comparable scale or sophistication in wartime Japan. Historians examining the Pacific War's technological dimensions have debated the significance of the automation gap that Komatsu's examination revealed. Some argue that tactical factors, pilot training, strategic decisions, force deployment, mattered more than technological sophistication. Others contend that automation advantages allowed American forces to operate effectively with less experienced personnel, a crucial factor as the war expanded and demanded rapidly trained replacement crews. The B-17 could be flown effectively by pilots with fewer training hours than Japanese bombers required, because its automated systems reduced workload and compensated for inexperience. This automation dividend allowed American training programs to focus on combat tactics rather than aircraft systems management, producing combat-ready crews faster than Japanese training programs could match. The broader lesson that emerged from the B-17 examination transcended specific technical details. The aircraft represented a holistic approach to aviation technology, where design, manufacturing, operations, and sustainment were considered as integrated elements rather than separate domains. American designers created systems that could be mass-produced, easily maintained in field conditions, operated by adequately trained crews rather than requiring exceptional skill, and sustained through standardized logistics networks. This systems engineering perspective reflected industrial maturity and organizational sophistication that were as important as any specific technological innovation. For Japanese aviation, the B-17 examination crystallized an understanding that many engineers and officers had suspected but found difficult to articulate. Japan had entered the war with tactical and operational advantages, superior fighter aircraft, better trained pilots, more extensive combat experience. But these advantages existed within a narrow window that was closing rapidly. As the war progressed, American industrial advantages would compound. More aircraft, more replacement pilots, continuous technological improvement, while Japanese advantages eroded through attrition and resource depletion. The automation technologies in the B-17 were not isolated marvels, but symptoms of an industrial system capable of continuous improvement at scale. The historical records preserved from Komatsu's examination, including detailed technical drawings and photographs that survived the war, eventually contributed to post-war Japanese aviation development. As Japan rebuilt its aviation industry during the occupation and beyond, engineers applied lessons from their wartime studies of American aircraft. The emphasis on automation, standardization, and mass production techniques that had seemed unattainable during the war became achievable goals during peacetime reconstruction. Modern Japanese aviation, with its reputation for precision manufacturing and sophisticated automation, traces partial lineage to the sobering lessons of that captured B-17. On February 4, 2003, exactly 60 years after the B-17's crash landing in Java, a small ceremony at the Japanese National Archives commemorated the historical examination. Historians presented papers discussing the technical intelligence work that Komatsu and his team had conducted, acknowledging both the thoroughness of their analysis and the painful implications of their findings. The event concluded with a reflection that the captured bomber, in its brief existence as a Japanese prize, had taught lessons about industrial capability, technological integration, and the material foundations of military power. Lessons that transcended its immediate wartime context and spoke to fundamental questions about industrial development and technological competition that remain relevant in contemporary times.